Good morning. Do you hear me?
Yes.
Okay, thank you. So we start now. You remember that we started discussing the issue of introducing dopants into the semiconductor lattice. And we already have pointed out that there are two different types of dopants. One is of N-type, and it is based on chemical species that belong to the fifth column of the periodic table of elements. A typical example for silicon is phosphorus, and this provides the so-called N-type doping. Also, atoms like phosphorus that give or donate electrons to the conduction band are also called donors. Okay, so a doping of the N-type is also called donor type doping. The other possibility is using a material belonging to the third column of the periodic table of elements. In this case, the typical example is boron. A boron atom provides a hole to the valence band. And in so doing, the boron atom captures an electron or accepts an electron in it. So for this reason, it is also called acceptor type dopant. And since the free carriers that are provided by the acceptor atoms are holes, and holes are positive, the type of dopant that is obtained with donor atoms is also called p-type doping. Now, after examining the situation in a space diagram or figure like this one, visible on the screen, we can repeat the analysis using the energy diagram. So in the next page, you can see the structure of the energies in the case of a N-type or donor type material. Okay, you remember the number of donor atoms is in any case much smaller than the number of silicon atoms in the crystal, or better, the concentration of the donors is small with respect to the concentration of the silicon atoms. So the dopant atoms are far apart from each other, so they do not influence very much globally the structure of the silicon lattice. The result is that if you calculate the bands for a doped semiconductor, you find substantially the same structure of the bands, that you would find for the intrinsic case. The only difference being that besides the bands that are the same as for the intrinsic case, there are also additional energy states available for the electrons. And when we use a donor type doping, these energy states are placed in the band gap in the vicinity of the edge of the conduction band. So if you look at the left part of the figure, you see the usual band structure with those little lines visible near the lower edge of the conduction band. Those are the additional states that are introduced by the donor atoms, and they are represented as the short lines to remind one that they are positioned in space at the location of the corresponding dopant atoms. Okay, so these states are not extended over the whole volume of the semiconductor, but they simply belong to the position in space where the donor atom happens to be. Okay. What is the distance of the, let's call them donor levels, okay? If you look at the right part of the figure, you see that the energy level of the donor atoms is indicated with symbol ED. And this value, ED, is just below EC. EC, you remember, is the position of the lower edge of the conduction band. The distance between EC and ED is very small. Typically, it is 0.03 electron volts. So it is a very, very small distance. What happens when you have these states? These states, of course, initially, if you think of, as we do usually, if you start from 0 Kelvin, the donor states, as you remember from the description in space, are filled because there is no energy enough for the electrons belonging to the phosphorus atoms to leave, to abandon the phosphorus atoms and left them ionized. Okay, so there is no enough energy. But if you go to a temperature that is above 0 Kelvin, sooner or later there will be enough energy in the crystal to be captured by the electrons belonging to the phosphorus atoms and make a transition into the conduction band. And this is very easy because the difference in energy is so small. So a very little energy is necessary for the phosphorus atoms to ionize. Another issue is, how do we describe the density of states? Well, the density of states of the bands is unchanged. It is just the same as for the intrinsic case. In contrast, we have an additional density of states that must be associated to the states of the phosphorus or the donor atoms, okay? And of course, the density of states for these atoms is positioned in energy over the value ED. So it is a function that is non-zero in the vicinity of ED, and immediately it becomes zero when we depart from ED. Okay, so if you look at the second part of the figure from the left, you see that stick, okay? that stick is the density of states of the donor states, okay? It is very thin in the vertical direction, so the energy interval where the density of states belongs is very short, okay? And the height that is in the horizontal direction depends on how many donor atoms we have in the semiconductor, okay? So it is intuitive that if we have to make some calculation involving that density of states, then we'll transform it into a delta function to ease the calculation. Another issue is this. You remember from the description that we have done last lesson that the number of electrons that is donated by the donor dopants may be much, much larger than the number of electrons of the conduction band that come from the transitions coming from the valence band, okay? So we expect that the population of the electrons of the conduction band in a donor type material and doped material would be much, much larger than the intrinsic case. This is actually true, and one of the outcomes of this is that the Fermi level, if you have an N-type material, the Fermi level is not anymore in the mid-gap of the semiconductor, but is shifted upwards. Okay, so if you look at the right-hand part of the figure, you see that EF is not anymore in the mid-gap, but closer to EC, okay, and far away from EV. As a consequence, if you look at the central part of the figure, the Fermi statistics is also shifted upwards, okay? So that means that the probability of occupation of the states of the conduction band becomes larger than the intrinsic case, and the probability of occupation of the holes of the valence band becomes smaller, okay? It follows that for the conduction band, the product gamma times P, I remind you that gamma is the combined density of states in energy and volume, times the Fermi statistics becomes larger than in the intrinsic case. So you can see that the area subtended by this curve, gamma times P, is larger than the intrinsic case. In contrast, the area of gamma times 1 minus P is smaller. So we have many more electrons and fewer holes with respect to the intrinsic case when we consider a semiconductor of the N-type, okay? As usual, we are for the moment considering a situation that is uniform in space. That means that the concentration of the dopant atoms is the same everywhere in the crystal. So there is no dependence of any function on position. So every property that we are discussing is the same at each position of the crystal. Now we discuss the dual situation, that is the situation of the acceptor type doping, like boron. In this case, it happens that the position of the additional states provided by the acceptor atoms is still in the gap, but very close to the lower edge of the valence band. So you can see from the second part of the figure from the left that the density of states again is a stick, but this stick is close to the edge of the valence band, and the central energy of the stick is called E sub A, as you can see on the right. Okay. Also, in this case, the distance between E sub A and EV, the edge, the upper edge of the conduction band, is of the order of 0.03 electron volts. Now, what happens, since the distance of the states introduced by the dopants from the valence band is so small, at a temperature that is different from absolute zero, it is relatively easy for electrons belonging to the valence band to make a transition into the states of the dopant, because they just need the energy of 0.03 electron volts. Okay, so very little energy. So in this case, these states capture an electron, and this transition of the electron from the valence band into the states leaves behind a hole. So this is the reason it is much better understood in this diagram than in a space diagram. Okay, these holes are left behind in the valence band, so that the valence band becomes richer of holes with respect to the intrinsic case. In this type of dope material, the Fermi level also shifts, but it shifts downwards. So if you look at the right part of the figure, the Fermi level is closer to the valence band than to the conduction band. It is no more near the mid gap. Okay. So this concludes the discussion when we have either a donor type doping or acceptor type doping alone. There is another comment that let's go back for a second to the case of the N-type semiconductor. You remember, when we introduce a phosphorus atom in the semiconductor, this atom is globally neutral, okay? And when, for instance, we are at 0 Kelvin, the phosphorus atom does not ionize, so it stays neutral, okay? So as long as the electron is inside the phosphorus atom, the atom is neutral. When the electron makes a transition into the conduction band, the phosphorus atom becomes positively ionized. So that means that the traps introduced by the donors are neutral when filled with the electron and become positive when empty of the electron. Okay, so they are neutral when filled, positive when empty. The opposite happens with the acceptor type dopants, because as long as we are, for instance, at 0 Kelvin, nothing happens. The boron atoms are neutral, okay? At larger temperatures, they capture one electron, so they become negatively ionized. So the acceptor traps are neutral when empty of an electron, negative when filled. Okay, so they are just opposite or dual with respect to the donor type traps. Okay, in real devices, we have at the same time both types of dopants in the semiconductor. So we have in the same position in space both acceptor and donor type dopants. Okay. In general, the distribution of the donors and of the acceptors depends on position. Okay, for the moment, we still consider the uniform case, and we may try to make a qualitative reasoning. Okay, if you start introducing first the n-type dopant, you remember the Fermi level will go up with respect to the intrinsic case, okay? But if at a later time you introduce the p-type dopant, then the Fermi level will go down, okay? And the question is who wins? Will eventually be found the Fermi level in the upper part of the gap or in the lower part of the gap. It depends on the concentration of the dopants. Okay, we shall see by calculation if the donor type doping prevails, so if the concentration of it is the larger, then the largest, then the Fermi level will be in the upper part of the gap. If instead the acceptor type concentration will be the largest, the Fermi level will be in the lower part of the gap. This figure here shows a particular case, that is the case of a perfect compensation. If you introduce an equal concentration of donor dopants and acceptor dopants, the Fermi level will stay in the same position as in the intrinsic case. This is intuitive, okay? Because if we introduce exactly the same amount of donor and acceptor dopants, then the Fermi level will go up and then will go down again by the same amount, okay? So it will not move eventually. So this is the situation of a perfectly compensated material in which the Fermi level is in the mid-gap like in the intrinsic case. Now the issue is we have to calculate again the concentrations, okay? But when you have a doped semiconductor, consider for instance first the case of the n-type semiconductor, okay? In this case, we must calculate not two populations, but three populations, because we have to calculate the concentration of the electrons of the conduction band, the concentration of the holes of the valence band, and also, since we have another family of states, we have to calculate the concentration of the electrons that are inside the donor state, okay? Of course, this population is expected to depend on temperature, okay? So we have to calculate three quantities, and we expect that the concentrations of the electrons in the conduction band and the concentration of the holes in the valence band will be different from the intrinsic case, Okay, we already understood this from the figures, okay? So instead of using the suffix Ni that indicates the intrinsic case, we shall not use any suffix, okay? So for the doped semiconductor, we call simply with small n the concentration of the electrons in the conduction band. As usual, we are considering a constant, a uniform case, so the dopant concentration is constant everywhere in the volume. So we can calculate small n as the total number n sub e of the electrons of the conduction band divided by the volume. And the calculation is formally identical to the intrinsic case. We must take the product of the density of states in energy times the probability of occupation, that is the Fermi statistics, and then we integrate over the conduction band, and then we divide by the volume. Okay, of course, we expect that this quantity will be different from the intrinsic case. Then we calculate P. Small p is the concentration of holes of the valence band, and the calculation is just as usual. We take the density of states, we multiply by 1 minus p, that is the probability of being empty of the state of energy E, and then we integrate over the valence band and we divide by the volume. So P will be different from Pi, and also NP will be different from each other, okay? For a donor type dopant, the population of electrons will be larger than that of the holes, okay? Finally, we calculate the concentration of the electrons that are in the donor states. We call it small n sub d, okay? And the calculation is just the same. We take the density of states of the donor states, GD, and of course this is the stick, okay, that you remember from the figure. Then we multiply it by the probability of occupation PD of the donor states. And then we integrate over the width of the stick that is called delta ED. Okay, it is the width along the energy axis of the stick that we have commented before. Okay. We can also make a reasoning. The number of electrons, sorry, the concentration of the electrons Nd that are present in the phosphorus or in the donor atoms, okay, this concentration of electrons can be thought of as the concentration of the dopant atoms that has not ionized, okay, because the electron is still in the atom, okay. So the concentration of the donors that has not ionized yet can be calculated as the total concentration of the donors that we call capital ND, as you can see in the third line of the page, less the concentration of the donor atoms that have ionized, okay? And this is called ND plus. The plus, to remind you that since they are atoms that have lost one electron, they are positively ionized, okay? So small nd is equal to capital ND, that is the total concentration, less the concentration ND plus of the ionized donors. When we perform the calculations for small n and small p, we have to use again the Fermi statistics. The Fermi statistics, you remember, it's written in the middle of the page. And in this case, the semiconductor is not intrinsic anymore because there is a dopant in it. So the Fermi level here is indicated with E sub f without the suffix I that in the intrinsic case reminds you that the semiconductor is intrinsic, okay? But apart from the symbol, the other definitions are just the same. So psi E is equal to minus ZE over KT, and ZE is the distance between the edge of the conduction band and the Fermi level. Similarly, psi H is equal to minus ZH over KT, and ZH is equal to the distance between the Fermi level and the upper edge of the valence band. So for the calculation of the concentration of electrons in the conduction band and the concentration of holes in the valence band, nothing changes with respect to the intrinsic case apart from the symbol E sub f instead of E sub Fe, okay? Of course, the numbers will be different, okay? So if you skip one line, you see that the density of states Ge of the conduction band is just the same as in the intrinsic case. So in conclusion, the concentration of the electrons of the conduction band will be Nc, that is the customary effective density of states of the conduction band, times the Fermi integral of order 1/2 of the argument psi E. So the difference is that the number, the numerical value of psi E is different from that of the intrinsic case. The same analysis can be done for the holes of the valence band. So we have GE is the in the line before the last. GE indicates the density of states of the valence band, and the concentration of holes in the valence band is NV, that is the effective density of states of the valence band, times the Fermi integral of order 1/2 of the argument psi h. So the calculation is identical to the intrinsic case, the numbers are different. But then we have an additional calculation to perform, the calculation of the population of the donor states, okay? So again, we have to use the Fermi statistics, but the Fermi statistics for the states introduced by the dopants is slightly different from the Fermi statistics used in the bands. Okay, so if you look at the equation that defines PD, okay, you see that PD, that is the probability of occupation of a state at energy E of the donor states, is a modified Fermi statistics in which the exponential has a coefficient that is expressed as 1 over small d, d with d, okay? Why is it so? The reason is that the first placements of the particles into the available states. The available states of the dopants are localized in space. So they are slightly different than those that are in the bands. Those in the bands are not localized in space. They are present all over the crystal, okay? So this difference introduces a difference in the placement and gives rise to the coefficient 1 over d sub d. This coefficient d sub d is called the degeneracy parameter, and in this case is equal to 2. Okay, so we have 1/2 exponential in the calculation of the statistics for the donor atoms. Okay, so we have a slight different form of the Fermi statistics. Then we have to take the form of the density of states, and that is the stick that we remember from the figure, okay? The stick is very thin because it is localized across the value of the energy state ED of the donor atoms, okay? So we replace the stick with the delta, Dirac delta, and you can see this in the last line. So we approximate GD as delta centered on ED, delta of E minus ED, times a coefficient, okay? What is this coefficient? Well, it is the concentration of the donor atoms, Nd, times the volume of the crystal. So this product, omega Nd, is obviously the total number of donor atoms of the crystal. Why is it so? Because if you integrate Gd over energy, since Gd is the density of states in energy, you must find the total number of states of the crystal, and each atom provides one state. So the total number of states of the donor atoms is equal to the total number of donor atoms, that is exactly omega Nd. So if you integrate Gd over energy, you know, remember that the integration of a delta gives you a 1. So the integration of omega Nd delta gives you omega Nd as should be. When you place this density of states into the integral, defining Nd, you remember one of the properties of the delta is that it blocks the other function in the integrand to the value of where the argument of the delta vanishes, okay? So the integration provides small nd is equal to capital Nd PD calculated at Ed. And finally, you remember that small nd is equal to capital Nd minus Nd plus. So you can extract Nd plus equal to Nd times 1 minus PD calculated at Ed. So you have the expression of all quantities involved in this calculation. You also remember that when you calculate a Fermi integral, okay, its value depends on the parameter that is the Fermi level, okay, because the Fermi statistics embeds the Fermi level in it, okay? And at the beginning of the calculation, the position of the Fermi level is not known. You remember, we already met this problem in the intrinsic case, okay? We perform the calculation using the Fermi level as a symbol, but eventually we must calculate the position of the Fermi level. The same is in this case, because the concentration of the electrons of the conduction band depends on psi e, and psi e depends on the Fermi level. The concentration of the holes also depends on psi h, that depends on the Fermi level, and Nd plus, that is the concentration of ionized donors, depends on Pd, and Pd depends on the Fermi level, okay? So we have three quantities whose values can be found only after determining the position of the Fermi level, okay? In order to calculate the position of the Fermi level, we replicate the reasoning that we already have done for the case of the intrinsic material. You remember, we started from absolute zero. At absolute zero, in the intrinsic case, all the conduction band is empty, the valence band is filled with electrons, and that's it. When we increase the temperature, one electron will eventually make a transition from the valence to the conduction band. So we shall have one electron in the conduction band, one hole in the valence band. When the second electron makes the transition, we have 2 and 2, and so on. Okay, so in the intrinsic case, we have equality of N and P. Now we come to the case of the dopant atoms, or the doped semiconductor. And we remember that we are in the uniform case. So every property of the material is the same at each position in space, okay? Now we start from again from the case of absolute zero. At absolute zero, all the states of the valence band will be filled. But also all the donor atoms will be filled with one electron, because there is no enough energy for the electrons of the dopants to transit into the conduction band, okay? So the concentration of the ionized donors at 0 Kelvin is 0. And obviously the conduction band is also empty, okay? Now, let's start now increasing the temperature, okay? Sooner or later, we'll find one electron in the conduction band. And the question is, where does this electron come from, okay? It may come from the donors, from one of the donor atoms, or it may come from the valence band, okay? If it comes from the valence band, it leaves behind a hole. If the electron comes from one of the donor atoms, it will leave behind an ionized donor atom, okay? So when we have many electrons in the conduction band, we may always state that a part of these electrons will come or has come from the valence band, leaving behind holes. And the other part of these electrons sitting in the conduction band came from the donor atoms, leaving behind ionized donor atoms. In conclusion, you may set up a balance relation of the form that you can see in the first line of the page. You may say that the total number of the electrons of the conduction band equals the total number of the holes of the valence band plus the total number of the ionized donors. Then you remember that we are considering a uniform semiconductor, So the concentrations in the uniform case are simply found by taking the numbers and dividing by the volume of the crystal. In conclusion, you obtain that the concentration of the electrons, small n, is equal to the concentration of holes, small p, plus the concentration Nd plus of the ionized donors. So this is the balance equation that applies when there is only the donor type doping and the material is in the uniform case and of course at equilibrium. Okay. At this point you just replace the expression. So small n becomes Nc times the Fermi integral of order 1/2 of psi e, and this is equal to Nv, the Fermi integral of order 1/2 of psi h, plus Nd times 1 minus Pd of Ed. Okay? And all these quantities depend on the Fermi level. Okay, so this is an equation in which eventually, of course, it is terrible to solve, okay, because the Fermi integrals are complicated to deal with, okay. Also, it is not possible anymore to make an estimate, because in this expression we also have the contribution of the donor, so it is impossible to make an estimate. The only way out is solving the equation numerically to find the position of the Fermi level. Okay. After that, assume that that somebody has done the numerical calculation for you. Okay. At this point, you may check whether it is still possible to approximate the Fermi integrals with exponentials. Okay, it may be possible or not. Okay, if it is possible to make this replacement, you remember this happens when the parameter psi of the that appears in the Fermi integral is smaller than -1. Okay. For the conduction band, this is equivalent to say that Ze is larger than Kt. But you remember Ze is equal to Ec minus Ef. So Ze larger than Kt indicates that the Fermi level is below Ec by at least 1 Kt. Okay, so Ef must be below Ec by at least 1 Kt. For the valence band, psi smaller than -1 implies that Zh is larger than Kt. That means that Ef must be above Ev by at least 1 Kt. Of course, if you consider the n-type dopant, the first condition is more difficult to fulfill, okay, because the Fermi level has gone upwards, so it is closer to Ec. So in order to apply the approximation, Ef should be not that close to Ec. Ef should be lower than Ec by at least 1 Kt. In contrast, the condition is very easy for the difference Ef minus Ev, because Ef has gone up, okay, so it is farther away from EV. We stop now for 10 minutes and we shall continue the discussion at 10:10.
Okay, so we start again. Okay, so you remember we have just seen the condition for which we can replace the Fermi integrals with the exponentials. We must have that simultaneously the Fermi level is below EC by at least 1 kT and above EV by at least 1 kT. If that happens, we may replace the Fermi integrals with exponentials. And of course, this makes life much easier. Among the other things, we have that the product of the two equilibrium concentration, so the equilibrium product of the concentrations, that in this case is NP, because N and P are different, you remember. When you take the product, it comes out to be exactly NC and V times the exponential of minus the gap over KT, because also in this case, the Fermi level that is inside psi E and psi H cancel each other. But if you look at this expression, it is just the same as Ni squared. So when we are allowed to use the exponentials, then the equilibrium product of the concentrations is equal to the equilibrium product of the intrinsic semiconductor, although N is different from Ni and P is different from Pi, okay? N is larger, P is smaller, but these differences compensate in the product, okay? Let's continue. Let's go back to the figure for a second, because we are still in the case of the N-type doping. We assume that EF is below EC by at least 1 kT and that EF is above EV by at least 1 kT. This condition, you remember, in which we can replace the Fermi integrals with exponentials, is called the non-degeneracy condition. So the semiconductor in this case is called non-degenerate, okay? You also notice from this figure that the distance between ED and EF is smaller than the distance between EC and EF, because EC is slightly above ED, okay? But assume that we also have the stronger condition that the distance between ED and EF is at least 1 kT. So assume that EF is below ED by at least 1 kT, okay? If that happens, you can simplify also the expression of the population or the concentration of ionized donors. Why? Because if EF is below ED, by at least 1 kT, that means that the exponent in this formula is negative and large. That means that it is negligible with respect to 1. So this function here, 1 over dd exponential, etc., is practically equal to 1. And this means that PD calculated at ED is negligible with respect to 1. Physically, that means that the probability of occupancy of the donor state is negligible. That is, the donor state are completely empty. All of them are empty because the probability of being filled is negligible. If this condition happens, that means that all donor atoms are ionized. So this condition is called complete ionization. And of course, if the atoms, the donor atoms, are 100% ionized, that means that the concentration of the ionized donors is equal to the concentration of the donors because they are 100% ionized. Okay? Conclusion: if this stronger condition occurs, this condition is called complete ionization. Okay, whereas the other one, as you remember, is called non-degenerate case. Okay. If we have complete ionization, then Nd plus becomes equal to Nd. This looks simple, okay, not so important, but it is important because Nd is a known constant. It does not depend on the Fermi level anymore. It's a constant. So the original balance equation that we started from, the one in the first line here, when Nd plus becomes Nd, it becomes simply N equal to P plus Nd, okay? And this must be coupled with the other information that the product Np is equal to Ni squared. Ni squared, of course, is something that we can easily calculate. Okay, we know the formula of Ni squared. Okay. In conclusion, when you have a uniform semiconductor in which the non-degenerate case occurs and also the complete ionization case occurs, okay, you can calculate algebraically very easily the concentrations of the electrons and holes. How do you do it? Well, take the balance equation and multiply both sides by small n. So n becomes n squared. Nd becomes Nd times small n. You bring it to the left. P becomes Np, but Np is equal to Ni squared because we are in the non-degenerate case. And if you look at this expression, this is just an algebraic equation of the second degree that you easily solve for small n. Conclusion: small n is equal to Nd divided by 2 plus the square root of Nd squared divided by 4 plus Ni squared. Okay, of course, in the general solution there is also a minus here, but you must neglect the minus because it would give you a negative concentration. This is non-physical. Okay. In the realistic cases, the concentration of the dopants, Nd, is much larger than the intrinsic concentration, okay? So under the square root, Nd squared is even larger than Ni squared. So you can neglect Ni squared. You obtain that the square root is equal to Nd 1/2, plus this one, it is equal Nd. So in conclusion, for a uniform semiconductor that is doped of the N-type, if you have the non-degenerate and complete ionization conditions, and the concentration of the dopants is larger, significantly larger than the intrinsic concentration, this is very easy, okay? Because the smallest concentration of dopants is of the order of 10 to the 14th per cubic centimeter. And if you are at room temperature, Ni is of the order of 10 to the 10th in silicon. So you already have 4 orders of magnitude, okay? So when all these conditions apply, then the concentration of the electrons in the conduction band, in the equilibrium condition, is practically equal to the concentration of the dopants. As you remember, we anticipated that the concentration of the dopants dominate, okay? The concentration of the holes is easily found because you remember that the product Np is equal to Ni squared. So P is equal to Ni squared divided by N. N is almost equal to Nd. So you have Ni squared divided by Nd, okay? Let's consider some orders of magnitude, okay? Take capital Nd, that is the concentration of the dopants, equal to 10 to the 15th, okay? Then the concentration of the electrons in the conduction band will be 10 to the 15th, okay? 10 to the 15th is small enough to have the non-degeneracy and complete ionization conditions to occur. So Nd is 10 to the 15th. If you are at room temperature, Ni is 10 to the 10th, the square is 10 to the 20th, divided by 10 to the 15th makes 10 to the 5th. So the concentration of holes is 10 to the 5th. So you have 10 orders of magnitude difference between the concentration of the electrons and that of holes. For this reason, the electrons in this case are also called the majority carriers, whereas holes are called the minority carriers. Okay. One question: what happens if we change the temperature, or what happens if we change the concentration of the dopants? Okay, we are still in the case of the donor type material. Okay, one should make the calculation. So one should simply recalculate the position of the Fermi level after changing the temperature or after changing the concentration of the dopants. Qualitatively, we may say this, that at constant temperature, increasing the concentration of the dopants in the N-type semiconductor will force the Fermi level to shift upwards. Okay, so as you increase the dopants, EF goes up. At some point, the distance between EF and EC will become smaller than EC, so we cannot use anymore the exponential, but this is of no importance. I mean, the concept is the same. When you increase the doping concentration, EF goes up in the N-type semiconductor. If you keep instead the doping concentration to a constant value and you increase the temperature, EF will go down, will try to go near the intrinsic value that is the mid gap, okay? If you instead decrease the temperature, EF will go up, okay? We shall see figures that describe this more precisely. These results, that is the position of EF with respect to temperature and with respect to the concentration of dopants, of course, must be calculated numerically in the general case. If we limit ourselves to the situation where the non-degeneracy and complete ionization conditions apply, that is the easy case in which we have ND plus equal to ND and the exponentials for N and P, then we can also calculate this analytically. So in order to understand what happens to the Fermi level when the approximation apply, we can do it much more easily because we have the exponentials at our disposal. So what you do is simply that you take the derivative of EF with respect to ND, and it comes about to be positive. So EF increases when ND increases. And if you instead calculate the derivative of EF with respect to temperature, you find that it is negative, okay? So EF goes down when you increase temperature, okay? Before we repeat the analysis, of course, the analysis is quite similar for the P-type doping, we must introduce a new symbol. Look at this line, okay? You remember in the definition of N, you have the exponential of EC minus EF, okay? You can play a little trick on this because the difference of EC minus EF can be written as EC minus the intrinsic level EFI plus EFI. Of course, you subtract and you add it again. And then you have minus E sub F, okay? Then you introduce a definition. The difference between the actual Fermi level and the intrinsic one with the minus is called Q phi F, where Q is the modulus of the electron charge, and phi F is a quantity whose units are volts, because you remember that an electric potential times the electric charge gives you an energy, okay? So phi F is called the Fermi potential and defines the displacement of the Fermi level of the actual situation with respect to the intrinsic situation. Okay? If you now take the exponential expression of the concentration, you remember it is Nc e to the minus Ec minus Ef over kT, and then you replace this definition here, you obtain an alternative expression of the concentration, that is the intrinsic concentration times the exponential of minus Q phi F over kT. Okay. Obviously, for the n-type doping, EF is larger than the intrinsic, so phi F is negative. This is obvious. Okay. So why do we do so? Why do we introduce this Fermi potential? Because later on, it will be much more convenient to use, instead of energies, to use electric potential. So we start introducing the electric potential that will soon replace the energies in the equations. For the p-type, the analysis is practically identical. So we calculate the concentration of the holes and of the electrons as usual. So they come about to be proportional to the Fermi integrals of psi e and psi h. So the actual difference between this case and the other case when the doping is of the n-type is that the position of the Fermi level will be different. Then we have to calculate the the concentration of the ionized acceptors. Okay, the ionized acceptors are of course negatively ionized, because you remember that the acceptors capture 1 electron each. Okay, so the population of the electrons of the concentration of the electrons in the ionized acceptors is equal to the concentration of the ionized acceptors. Okay. The density of states for the acceptors is, of course, you see it in the last line, omega Na, where Na is the concentration of acceptor atoms, times the Dirac delta centered at E sub A, that is the position of the energy levels of the acceptor atoms. The occupation statistics is a modified Fermi statistics that we call P sub A, in which again we have a degeneracy coefficient. In this case it is called dA, but its value is still equal to 2. Okay. So in conclusion, we have that Na minus, you see it in the last line, is equal to the concentration of the acceptor atoms times the probability of occupancy calculated at E sub A. Again, we must impose a balance equation. In this case, the balance equation is if we have one hole in the valence band, this hole may derive either from a transition of one electron into the conduction band, or from the transition of one electron into the acceptor atom. In conclusion, the concentration of the holes must be equal to the sum, you see it in the next page, must be equal to the sum of the concentration of the electrons in the conduction band plus the concentration of the ionized acceptors. Okay, so again, we have a rather complicated equality involving the Fermi level. We solve it numerically, and then we check whether the exponential approximation is applicable. The conditions are just the same. Again, we must have E sub f, the Fermi level, above the valence band by at least 1 kT, and at the same time, EF must be below EC by at least 1 kT. Okay, so if we look in the figure, for the acceptors, you see that the distance between EF and EC is easily found to be larger in this case than kT. The difficult side is EF minus EV. This difference must be larger than kT. If that happens, we can replace the Fermi integrals with exponentials, and we have the non-degeneracy condition. If we have the stronger condition that EF is above EA by at least 1 kT, we can also have the condition of complete ionization. That means that all acceptor atoms have captured 1 electron, so they are 100% ionized. That means that the concentration of the ionized acceptors is equal to the concentration of the acceptors. Okay? So the concentration of the ionized acceptors is called Na with a minus because they are negative. In the complete ionization condition, P sub A is equal to 1. Here, so that Na minus is equal to Na. And again, we have a simple balance equation that can be reduced to an algebraic equation. In this case, we multiply by P. P becomes P squared. Na becomes NaP and goes to the left. N becomes Np, that is Ni squared. Also in this case, of course, the product of the equilibrium concentration is equal to Ni squared. This is an algebraic equation from which we obtain P. P is given by this expression, and if the concentration of the acceptor is larger than the intrinsic one, P is practically equal to Na, so the holes in this case are the majority carriers, and instead the electron concentration is Ni squared over Na, and the electrons are the minority carriers. What happens in a P-type semiconductor when we change either the temperature or the concentration of the acceptors? If we keep the temperature constant and we increase the concentration of the acceptors, EF shifts downwards. Okay, so when you increase the dopant concentration in the p-type case, EF goes closer and closer to the valence band edge. Okay. Instead, if you increase temperature while keeping the acceptor concentration constant, if you increase temperature, EF goes towards mid-gap. Okay. If the approximation of non-degeneracy and complete ionization is applicable, the analysis of the dependence on the Fermi level on temperature and dopant concentration can be done analytically as before. So for the p-type doping, you find that the derivative of EF over Na is negative. In fact, EF goes downwards. The derivative of EF with respect to T is positive. Okay. We introduce the Fermi potential. The definition is identical to the other case. Okay. It's just the displacement of the Fermi level with respect to the intrinsic one with a minus, okay, and divided by the electric charge. Of course, for a p-type semiconductor, the Fermi potential is positive, okay, and the concentration of the holes takes the expression Ni exponential of Q phi f over Kt. You see, phi f is positive, so the exponential is larger than 1, P is larger than Ni, as we expected in a p-type semiconductor. For the n-type semiconductor, N would be larger than Ni. Okay. Now we have to consider the case with in which both types of dopants are simultaneously present in the semiconductor. But before that, I just want to show you a couple of pictures. So this figure is taken from the reference Z. The author is Z, SZE. And it shows, let me zoom in a little. Okay. This is an Arrhenius plot of the concentration of electrons in a semiconductor uniformly doped with, you see, the concentration of dopants is 10 to the 15th donors per cubic centimeter. Okay. And remember, the Arrhenius plot has in the horizontal axis 1 over T or 1000 over T. So in this case, we have 1000 over T. And in the vertical axis, there is the log of the concentration, okay? So the continuous curve describes the concentration of the electrons of the conduction band as a function of temperature, okay? The portion of the curve that is practically horizontal and is called the saturation range corresponds to the temperatures in which the non-degeneracy and complete ionization conditions apply. In fact, you remember that in these conditions, the concentration of the electrons is practically equal to the concentration of the dopants. In fact, you see that the saturation range corresponds exactly to 10 to the 15th here, and we have a dopant concentration also equal to 10 to the 15th. So we have small n equal to nd, okay? And if you look at the horizontal axis, okay, you see that we have 1000 over T, okay? So 4 means 250 Kelvin, okay? Slightly below 0. And 8 corresponds to 125 Kelvin, okay? And if you go a little bit to the left of 4, you have room temperature, okay? So this graph shows that you have an interval of temperatures that is around room temperature, okay, in which the concentration of the electrons is substantially independent of temperature. This is a fundamental result. You remember, we anticipated that introducing the dopants first makes the conductivity controllable, because the concentration of electrons in the conduction band or the concentration of holes in the valence band is controlled by the dopants and not by the semiconductor. And second, this conductivity, at least in a range, in a useful range of temperatures, is independent of temperature, okay? So this is a fundamental result. When you decrease the temperature, so when you go to the right in this diagram, okay, it happens that not all dopants are ionized. Some of them do not find the energy that is necessary to ionize. So some of the electrons that are in the dopant atoms cannot perform the transition into the conduction band. They stay in the dopant atoms, and the fraction of them becomes larger and larger as you decrease temperature. So in this case, we say that the dopants are frozen, and this part of the curve is called the freeze-out range, okay? And substantially, the number of electrons in the conduction band will be lower than in the saturation range. If instead we increase the temperature, you remember, after a donor atom has provided one electron to the conduction band, it is impossible for it to provide a second electron, okay? So when the dopants are fully ionized, they don't change anymore. But instead, if you keep increasing the temperature, so you go to the left in this diagram, silicon will continue to produce electron-hole pairs. And if you remember the Arrhenius plots of the intrinsic silicon, when you reach about 1000 Kelvin, the intrinsic concentration is 10 to the 18th, okay? So at large temperatures, the intrinsic concentration, that is the electron-hole pairs provided by silicon, will dominate again with respect to the dopants, okay? And the contribution of the dopants will become unimportant. So at large temperatures, the semiconductor will behave as if it was intrinsic, okay? So for this reason, the rightmost part of the continuous curve is called the intrinsic range and is substantially coinciding with the dashed curve that instead describes the concentration of the intrinsic case. That is the Arrhenius plot of the intrinsic case. Okay. Another figure is this. Sorry. This new figure shows a set of curves that describe the position of the Fermi level for a number of possible values of the dopant concentration and for different temperatures, okay? So the horizontal axis is the temperature in Kelvin. The vertical axis is the difference between the Fermi level and the intrinsic level. So the zero is at the mid gap in this case, okay? Then you see that there are these areas below and above indicated with valence band and conduction band. So this line here is the lower edge of the conduction band, and this other line here is the upper edge of the valence band. You see that at 0 Kelvin, this is silicon. At 0 Kelvin, the gap is 1.2 electron volts, okay, because it is minus 0.6 below and plus 0.6 above, okay? And you remember, when you increase the temperature, the gap decreases. In fact, you can see that the edge of the valence band goes up and the edge of the conduction band goes down, okay? Then you have many curves. Of course, these curves must be considered one at a time, okay? So, for instance, consider this one, a curve that is labeled 10 to the 16th, okay? It is the position of the Fermi level for an N-type semiconductor, an N-type silicon. So the Fermi level is above mid-gap. But when you change the temperature, if you go to the right, the Fermi level will approach zero. That is the intrinsic situation, because you remember at high temperature, there are so many electrons and holes produced by silicon that the material behaves as if it was intrinsic, okay? Instead, when you decrease temperature, the Fermi level goes up, and at some point, it is not shown in the figure, the position of the Fermi level at 0 Kelvin will be between EC and ED, so that it will be below EC, so that the conduction band will be empty, but it will be above ED, so that all the donor states will be filled. Okay. The same if you consider a p-type doping, and again you take the 10 to the 16 curve, it is always below the intrinsic Fermi level. It tends to the limit of the intrinsic when temperature increases, and instead it tends to the to a position between EA and EV when temperature goes to 0. On the contrary, if you fix temperature, like 300 Kelvin, this vertical line here, and then you change the dopants, you see that the Fermi level, consider the n-type situation, the Fermi level is a little bit above the intrinsic value for 10 to the 12. It goes up 10 to the 14th, 15, 16th, and so on, and then the semiconductor will become degenerate of the n-type. The same happens for a p-type dopant, just the opposite. When it is 10 to the 12, it's slightly below the intrinsic, and then it goes down and down when you increase the dopant concentration. Okay, so this shows this figure also is taken from Z. Now we go back to the slides. And we must consider the case in which both the donor and acceptor dopant concentrations are present at the same time, but still with the uniform concentration. Now it is very late, it is almost 11, so we stop here. If there are questions, you can open the microphone, and then we shall start again at 11:10. Okay. We can start again. So remember, we were left with the case of a semiconductor in which at the same time both donor and acceptor dopants are present, but we still consider the situation where the material is uniform in space. So both concentrations capital ND and capital Na of dopants are constant. The calculation is identical to the other cases, so there is absolutely nothing new. The concentration of the electrons is proportional to the Fermi integral of order 1/2 of parameter psi e. That of holes is NV times the Fermi integral of psi h, ND plus as the old expression as before, ND times 1 minus PD, calculated at ED. And finally, NA minus is equal to NA times PA of EA. How do we set up now the balance condition? As before, you remember, we may say that if an electron goes away from the valence band, it may end up either in the conduction band or into an acceptor atom. And similarly, if there is one electron in the conduction band, it may come either from the valence band or from a donor atom. So globally, the balance equation reads, as you can see in the third line of the page, N plus Na minus must be equal to P plus Nd plus. This can also be understood in a different way, that is, the concentrations of the negative charges, that are the electrons and the negative and the ionized acceptors that are negative. Okay, so electrons are negative and the ionized acceptors also are negative, are equal to the concentrations of the positive charges, that are the holes, and the ionized donors, that are positive, okay? More generally, you can think that since the semiconductor is globally neutral, the total number of positive charges must balance the total number of negative charges. But then, since the semiconductor is also uniform, you easily go from the total numbers to the concentrations by dividing by the volume of the crystal, okay? So the balance equation essentially means the number of negative charges is equal to the number of positive charges, okay? Again, one should replace to each expression of the balance condition the corresponding expression in terms of the exponentials or the Fermi integrals, okay? And then calculate the position of the Fermi level, okay? It is also possible to make this observation. You can define a quantity that is indicated with capital N, and this quantity is the net ionized doping concentration. Net means donors minus acceptors. Okay, so N is defined and ND plus less NA minus. Okay. Depending on the concentration of the dopants, this capital N may be either positive or negative. Okay. If the donor concentration prevails, it is positive. If the acceptor concentration prevails, it is negative. So assume that it is positive. In this case, if you look at the left, you can write the balance equation N as small n equal to small p plus n. So when n is positive, that means when the donors prevail over the acceptors, the balance equation becomes identical to the balance equation for a crystal that is doped only with donors. However, you use capital N, that is the difference between donors and acceptors. If instead N is negative, then minus N is positive. And you can write the balance equation like in the middle of the equations, like N minus capital N equal to P, in which minus N is positive. So the form of the balance equation in this case takes the form that is typical of the p-doped semiconductor. Okay, again, you are using only the net concentration. So this is called the compensation effect. It is a partial compensation because in general ND plus is different from NA minus, so capital N is non-zero. Okay. The compensation effect tells you that if the donor type of doping prevails, then the semiconductor behaves as if it was doped only of the donor type with the concentration equal to the difference. If instead N is negative, the compensation effect tells you that when the acceptor concentration prevails, then the semiconductor behaves as if it was doped with acceptor atoms only, with the concentration equal to the difference. Okay. The example that we have shown in the figure before consider the case of perfect compensation, that is N, capital N equal to 0, which is a very special case, of course. If you calculate again the position of the Fermi level and you find out that the non-degeneracy condition applies, again you can use the exponentials. And again, you find that NP, the product of the equilibrium concentrations, is equal to Ni squared. If, moreover, the complete ionization also applies, you can let ND plus equal to ND and NA minus equal to NA. Okay? Which means that the net dopant concentration is simply ND
minus Na. Okay? In this case, it is possible again to find the algebraic equation from which you extract the concentration of electrons and holes. If you have a case in which the donor concentration prevails, okay, so N is positive, one must calculate the concentration of the electrons using the algebraic second degree equation that is visible in the first line. And again, one obtains small n equal to capital N half plus the square root. If instead one has the case in which the acceptor donor, the acceptor concentration prevails, one must calculate the concentration of holes, again using the algebraic equation, to find P equal to minus N half, but N, you remember, is negative in this case, plus the square root. In these cases, it is not obvious that the square root can be further simplified, okay? Because it may happen that the doping concentrations are not so different, so capital N is small, okay? But if capital N is large, much larger than Ni, we can further simplify the expressions by simplifying the square root. So when N is positive and the concentration of electrons will be equal to capital N, the electrons will be, of course, the majority carriers, and the concentration of holes will be almost equal to Ni squared divided by N, and the holes will be the minority carriers. The Fermi level will be above the intrinsic, and the Fermi potential will be negative. If instead the acceptor concentration of dopants prevails over the donors, then N is negative, minus N is positive, and if minus N is also larger, much larger than Ni, we shall have that the concentration of the holes will be equal to the absolute value of capital N, and the holes will be the majority carriers, and the electrons will have a concentration equal to Ni squared divided by the absolute value of N, so the electrons will be the minority carriers, the Fermi level will be below the intrinsic, and the Fermi potential will be positive. So this concludes the analysis for the case in which the concentration of the dopants is uniform. This case is non-realistic. It is useful because it was easy to go through all calculations, okay, but it is non-realistic because in the standard processes of semiconductors, the dopant profile depends on position. So we must now go to the case in which the dopant profile is non-uniform. From the formal point of view,
There is little change actually, because assume that the concentration of the donor atoms is some function that depends on position. Of course, this function is known to us because we manufacture the semiconductor device, okay? And similarly, the concentration of the acceptor atoms is also given as a function of position, okay? Since we are in the equilibrium case, we expect that we can still use the Fermi statistics. This is true. On the other hand, we also expect that the Fermi statistics must depend on position. So the issue is what kind of changes should be introduced into the Fermi statistics when we have a non-equilibrium condition. The change is very easy. If you look at the Fermi statistics here, you see that the only change is that instead of having the exponential of E minus the Fermi level, we have the difference, the exponential of the difference of the energy minus a function of position that we call EF with the bar on top. So the bar is not easily visible, so I'm going to amplify the page to make it more visible. You may see now that this E sub F has a bar on it, okay, to distinguish from the constant Fermi level of the uniform case, okay? So we have to replace a function that we call EF bar, and this function depends on position, okay? Of course, we don't know the function EF bar. It's like in the old case, we have a Fermi level, but we don't know it, we must calculate it, okay? Similarly, we have this function EF bar, but we don't know it. We shall be able to calculate this function later, okay? But you may also observe that when you calculate a concentration, what you do is actually integrating over energy, okay? So it doesn't really matter whether here you have a constant or a function, because you are integrating over the other variable energy when you calculate the concentration. So the point is that to calculate the concentrations in the non-uniform case, we simply repeat the same procedure as we did in the uniform case. We take the density of states, multiply it by the Fermi statistics, and then we integrate over the conduction band. What we find is an expression of the concentration that is, again, the effective density of states NC times the Fermi integral of order 1/2 of some parameter psi e that depends on position, because the original Fermi statistics also depends on position. So formally nothing changes. Similarly, we have P of R equal to the Fermi level of psi h of R. And for the acceptor, ionized acceptor or donors, we have ND plus depends on R, because first of all, the concentration ND depends on R, and also because the statistics depends on R.
Finally, the concentration of the ionized acceptors, Na- will depend on position, because both the coefficient Na depends on position, but also because the statistics depends on position. So formally, nothing changes. We simply have dependencies on position everywhere in the equations, okay? Now, the issue is when we consider the case of constant dopant, at the end, we found the position of the Fermi level by imposing the balance condition, okay? The question is, can we impose the balance condition also in this case? And the answer is unfortunately not. Why cannot do it? Okay, I'll give you an example. I think I have a figure, but I'm not sure that the figure is in this disk. I may show it to you the next time. Consider a non-uniform case, okay? And for simplicity, consider a situation in which the only dopants are of the donor type, okay? Now, assume that at some physical position of the semiconductor, the donor atoms are many, say 10 in a small volume of the crystal, okay? And assume that all these 10 donor atoms release 1 electron each to the conduction band. So you will have 10 electrons in a position in the conduction band. Then assume that in a nearby position, there is just 1 donor atom, okay? And this donor atom releases 1 electron into the conduction band. So you have 2 positions of the conduction band. In one position, you have 10 electrons. In the other one, you have 1 electron, okay? All these electrons are free to move, okay? And you know that there is a transport mechanism that is called diffusion. And diffusion qualitatively is such that particles that can move tend to move from the places where there are many to the places where there are fewer, okay? So the 10 electrons will start moving to the position where there is only 1 electron, okay? But the donor atoms cannot follow because they are fixed. So at the original position of the donor atoms, there will be a net positive charge due to the donor atoms, because this charge is not compensated anymore by the 10 electrons, because the 10 electrons have moved away, okay? So there will be a distribution of charge that is unbalanced in the semiconductor, okay? After some time, this motion of particles will stop, because when you unbalance the charge, you create a field, and the field will oppose to any further motion of the charge. We shall see it better later, but this is just a qualitative explanation, okay? So at some point, you will have an equilibrium condition that is restored, but there will be no compensation of charge anymore. There will be positions in the crystal that will be negative, because negative charges will prevail, and other position will be positive, okay? So in a non-uniform case, it is not allowed anymore to impose a balance condition because such a balance is not there anymore. We may instead say that there will be a non-zero net charge locally in the semiconductor. And this non-zero charge is given by the expression of the charge density that you can see at the bottom of this page, okay? At each position in the semiconductor, the total number or the total concentrations of the positive charges, P and D plus, will not compensate the total concentration of the negative charges, that is N and an A minus, okay? So the quantity in parentheses is non-zero in general at each position in the semiconductor when the semiconductor is non-uniform, even at equilibrium. If you multiply the parentheses by the electron charge, okay, because each hole is positive, it gives you a charge equal to Q. Each electron is negative, so you have Q with the minus near the electron. Nd plus are positive and Na minus are negative. Okay, so if you multiply the parentheses by Q, you obtain the charge density at each position of the semiconductor, and this will be in general non-zero. Okay, of course, this charge density is unknown because all quantities in the parentheses depend on the function EF bar, and this function is in itself unknown, okay? So it looks like we are in trouble because it is impossible for us to set up a balance equation, and we also have to find not a constant like we did in the uniform case. We have to find a function, the function EF bar, okay? And an idea about how to proceed comes from this observation. When you have to find a constant, you try to set up an algebraic equation. And the balance equation, in some sense, is an algebraic equation. When instead you have to find a function, well, a function is found by solving a differential equation, okay? So the idea is, in order to find a function EF bar, we should set up a suitable differential equation whose solution provides us with this function EF bar, okay? Another idea may come from the observation that the non-uniform case produces a non-uniform charge density, okay? And a field inside, an electric field inside the semiconductor. So we should solve some problem that should be able to provide the field and the charge density, and intuitively this is solving the Poisson equation, because the Poisson equation is such that eventually we can find the field out of it. So we expect that function EF bar should somehow be related to the electric potential in the semiconductor, okay? Neglect the first part of the equations. Okay, so I'm hiding it can be demonstrated that the function EF bar is equal to a constant. This constant is provisionally called EF bar up 0. Okay? Minus a function that we call U, where U is the electrostatic potential energy of the electrons. So U is an energy, okay? By the way, you remember that the electrostatic potential energy of the electrons is related to the electrostatic potential, phi, okay? The relation is very easy. U is equal to minus Q phi, okay? So the relation between function EF bar and the electric potential is found. Okay, you simply replace minus U with minus Q phi, and that's it. Okay. What is this can be demonstrated? Okay, we assume that somebody else has carried out the demonstration and we have this result. What is the meaning of the constant EF bar up 0? That constant is simply the value of the function F bar, EF bar, sorry, at the point in space in which U is 0. Okay? If you find this point, then, of course, the constant will become equal to EF bar of 0. On the other hand, you remember the 0 of the potential energy can be placed arbitrarily in any position. Okay, so this is not a big deal. The symbol EF bar up 0 is inconvenient, so we change it and we call it EF again. So essentially, function EF bar is equal to a constant that we keep calling Fermi level plus Q times the electrostatic potential inside the material. So if you succeed in finding at every position of space the electrostatic potential or the electric potential, okay, then you find EF bar, and then going back to the other pages, by the suitable integrations, you find the concentration of electrons, holes, and ionized donors and acceptors. Again, this page is very important. Again, you can check whether the non-degeneracy condition apply, but in this case, you must check it at each position of the semiconductor, because you have to do it instead of using the constant EF, you have to do it using the EF bar function at its position in the semiconductor. If the check of non-degeneracy is fulfilled at each position in the semiconductor, then it means that at each position in the semiconductor, EF bar is below EC by at least 1 kT, it is above EV by at least kT. Neglect the next two lines because they refer to a phenomenon that we are not going to discuss. Okay? So, if all of this is applicable, then you have that the difference EC minus EF bar, if you replace, you remember, EF bar is equal to EF minus U. So you can use this expression. EC I is equal to EC in this slide. Similarly, EF bar minus EV can be written as EF minus EV minus U, inserting that into the exponents. You have the general expression of the concentrations of the electrons and holes in a situation in which the dopants depend on position, but the non-degeneracy approximation is applicable. So you have exponentials in which, besides the usual EC minus EF, you also have the electrostatic energy of the carriers. Okay? At this point, we start performing the transformation. You remember we anticipated this earlier, that it is preferable to replace the energies with potentials. Okay? So, consider the two general expressions of N and P and specify these expressions in the position of space in which U is equal to 0. Okay? So when U is equal to 0 here, the corresponding value of the concentration is called N up 0. So N up 0 is the value of the concentration of the electrons in a position of space in which the potential energy is equal to 0. Of course, you are left with NC exponential of EF minus EC. But we already met an expression like this, and after some manipulation, you remember, due to the introduction of the Fermi potential, we have that N up 0 can be written as Ni exponential of minus Q phi f over kT. Then you go to the second expression, the expression for the holes. Again, consider the position in space in which U is 0, and the corresponding value of P is called P up 0. And by the same analysis, you find that P up 0 is equal to Ni times the exponential of Q phi f over kT. Okay? Now, you can use the expression of N up 0 and P up 0 into the general expressions of N and P. Okay? And you also remember that U, that is the electrostatic energy, is equal to minus Q phi. You remember at some point in a previous slide, we found this equality, this one. Sorry. This one. U is equal to minus Q phi. So we can also make the replacement of energy with potential here. So minus U is equal to plus Q phi. And here you have U that is equal to minus Q phi. So we get this. the two general expressions above become n is equal to n up 0 exponential of q phi over kt. And in the last line, p is equal to p up 0 exponential of minus q phi over kt. Okay, so this is a pair of useful expressions for n and p. Alternative expressions are obtained using the form of n up 0 and p up 0 that you can see above. So after the replacement, you have that n is equal to ni exponential of q phi minus phi f over kt, and p is equal to ni exponential of q phi f minus phi over kt. Okay? Remember, at this stage of the analysis, the electrostatic potential phi is still unknown. These are manipulations of symbols, okay, that provides you with some better symbols for n and p. But the electrostatic potential phi is yet to be found. It is some function of position that we don't know yet, okay? However, these two expressions are very, very important because they show you that in the general case in which the dopant concentration depends on position, but we are in the equilibrium condition, because we have been using the Fermi statistics to come to this point. Okay, so we are in equilibrium. Then the concentration of electrons and the concentration of holes are known functions of phi. That means that in the equilibrium condition, if we succeed in calculating phi at each position of the semiconductor, then we can calculate n and p at each position in the semiconductor, because all the remaining quantities in the formulas are parameters. Okay? So the issue is to find the electrostatic potential, but we anticipated that the differential equation that provides the electrostatic potential, as you remember, is the Poisson equation. We are going to see it soon. It is after many other pages that we are going to skip, so I'm now skipping a number of pages. Okay. We have little time now because we are almost at noon. So we anticipated that in order to find the electric potential, we must solve the Poisson equation. But you also remember that the Poisson equation is one of the Maxwell equations, okay? So we have just time to start a little resume of the Maxwell equation, okay? And then we shall continue on Thursday. As you remember, the Maxwell equations are divided into two groups. One group connects the field with the sources of the field. So the two equations of the first group are the divergence of the displacement vector D is equal to the charge density rho. Okay, so the charge density is one of the sources of the electromagnetic field. The second equation of the first group is that the rotational of the magnetic field H is equal to the time derivative of the electric displacement D plus the current density J, and the current density is the second source of the electromagnetic field. How do we write down the charge density? In general, what we do is we express the charge density as the sum of all the possible different types of contributions to the charge density. So the charges of type 1 have a concentration equal to rho 1. Those of type 2 have a concentration, a charge density rho 2, and so on. In a semiconductor, rho 1 could be like the concentration of holes times Q. Rho 2 could be the concentration of electrons times minus Q, and so on. Similarly, the current density is the sum of all possible contributions to the current density. In order to provide a contribution to the current density, the charges must be able to move. So, for instance, dopants don't move. So dopants do not contribute to charge density, only electrons of the conduction band and holes of the valence band, okay? So if the type 1 of charges is able to move, then its contribution to the current density will be rho 1 times V1. V1 is obviously the average velocity of the charges of type 1 whose charge density is rho 1. Then we may have another type, rho 2, with an average velocity V2, and so on. The total current density is the sum of these contributions. The second group of the Maxwell equations does not relate the fields with the sources, but it gives relations among the components of the fields themselves. And the two equations of the second group are the divergence of the magnetic induction B is equal to 0, and that the rotational of the electric field E is equal to minus the time derivative of B. You see, there are no sources in these two expressions, simply relations between components of the fields. So it's now noon, so we stop here. If there are questions, we may ask them now. Otherwise, we shall see or shall meet each other on Thursday afternoon.